There's a chance that when we push that button, we destroy the world. Chances are near zero. Near zero. What do you want from theory alone?
This is the mathematics that Oppenheimer and his team used to check if the first nuclear bomb test would end up destroying the entire world. Published in 1946, unclassified in 1973. The fear was that the extreme temperature from the blast would trigger a thermonuclear reaction in the atmosphere, fusing the nitrogen atoms in the air into magnesium. The reaction would quickly spread across the globe, turning the atmosphere into a plasma, destroying the Earth and all of its inhabitants. For the reaction to spread, the energy produced from nuclear fusion in a given region needs to exceed the energy lost within that region. The energy produced by the reaction depends on the density of nitrogen in the atmosphere, the probability of nuclear fusion, and the energy released per reaction. Oppenheimer's team had good estimates for the density of nitrogen in air and the energy released per reaction, but they had no experimental data for the probability of nitrogen atoms fusing. They assumed the worst-case possibility, that every collision would result in fusion. Using numerical integration, they obtained this curve, which shows the energy released per nucleus per second as a function of temperature. Next, Oppenheimer's team computed the energy lost as the reaction proceeded. At the incredibly high temperatures required for fusion, electrons break free of their atoms, forming a plasma. As electrons are slowed by interactions with the sea of ions, they release significant amounts of radiation known as Bremsstrahlung, or breaking radiation. The amount of energy released depends on the charge of the ions, in this case Z=7 for nitrogen, and the average velocity of the electrons, including relativistic effects due to the high speeds involved. Oppenheimer's team had reasonable estimates for these values, computing electron velocity using the energy transfer rate from nuclei to electrons. Using these equations, they obtained a second curve, showing the energy lost as a function of temperature. Now, in theory, by comparing these two curves, we can figure out if the world is going to explode or not. If for any achievable temperature, the energy produced is greater than the energy lost, the reaction will become self-sustaining and spread across the globe. Fortunately for Oppenheimer's team, the loss curve is greater than the production curve across all possible temperatures. However, as temperature increases, notice how uncomfortably close these curves become. Around 10 mega-electron-volts, the margin of safety becomes only 1.6, meaning that if scientists underestimated the gains by just 60%, the outcome would be completely different. Thankfully, there's another important consideration here. 10 mega-electron-volts is really, really, really hot. Electron volts are a measure of energy, not temperature, but it's convenient in plasma physics to express temperature in this way. That's what Oppenheimer's team is doing here. We can convert degrees Kelvin using the Boltzmann constant. 10 mega-electron volts is over 100 billion degrees Kelvin. Nuclear bombs release huge amounts of energy. But for the air to reach these incredibly high temperatures, that energy has to be transferred to air particles. The most significant transfer mechanism is collision with high-energy alpha particles released by the explosion. Due to the low density of air and the small size of nitrogen nuclei, it takes on average 57 meters for an alpha particle to collide with a nitrogen nucleus. This means that the volume of air required for the bomb to efficiently transfer energy is large, roughly a sphere of 57 meters. Heating a sphere of this size to 10 mega-electron volts requires an enormous amount of energy, around 100,000 times more energy than would be released by the fission bombs Oppenheimer's team was designing. This result, along with some other expected energy loss mechanisms, such as the inverse Compton effect, gave Oppenheimer's team the confidence to move forward with building and testing the first nuclear bomb. As the story became public knowledge in the decades after the war, a couple publications oversimplified and misrepresented the mathematics. A 1959 article in American Weekly incorrectly claimed that scientists computed a slightly less than 3 in 1 million probability that the world was going to end, giving them the confidence to move forward. Hans Bethe, a key member of Oppenheimer's team, responded in an essay, stating that this was never a matter of probabilities and that ignition is simply impossible. This is a more accurate representation of the mathematics, but there were clearly significant concerns at the time, and a number of uncertainties with the physics. Bethe may be being overly dismissive here, 30 years after the first nuclear bomb test. When Oppenheimer discovered the possibility of setting off a fusion reaction in the atmosphere, he immediately traveled by train to meet with his Manhattan Project supervisor, the physicist Arthur Compton. This matter was far too sensitive to discuss over the phone, and Manhattan Project leaders were not permitted to travel by plane. At the time, Compton was vacationing with his family in northern Michigan. Compton picked up Oppenheimer at the train station, and they drove to a nearby lake to discuss. Compton was deeply concerned. Recalling the conversation in his memoirs, he writes, "This would be the ultimate catastrophe. Better to accept slavery to the Nazis than run a chance of drawing the final curtain on mankind." Ultimately, this mathematics convinced Compton, Oppenheimer, and the rest of the Los Alamos scientists that the bomb they were building would not destroy the world.